As you'll see in the next couple of videos, we're really finished with finding areas and volumes using calculus, using integration. However, before integration, mathematicians were still calculating the area under curves. They were doing it in a very complicated way. We know that before calculus, mathematicians were working out the slope of curves, and we looked at that and we called that differentiating from first principles. We don't actually go that much into the actual process of finding area under curves because the mathematics involved is far more difficult than the mathematics for differentiation from first principles. However, we need to have some understanding of of what the process actually was. So if you think about finding the area under a curve and the tools that the mathematicians had pre-calculus times, then they would have been thinking about using their area formulas, obviously. If I just switch to the textbook, it actually nicely shows some diagrams here. So in the first diagram, you can see they've got the curve y equals x squared. And they've said, well, if we were trying to find the area under y equals x squared, then what we could do is, I suppose the worst case scenario is just say, well, that area would be the area of a, can I write on this? No, hang on. The worst case would be, I'll go back to the notes, that I've got y equals x squared here, and I want to know this area. I don't know the area under a curve, but the area of the rectangle would be its length times its breadth. And this height, by the way, is f of x. So if I want to know the area from 0 to 1, so its length, in terms of it being a rectangle, is 1 times its height. And if it's on the curve y equals x squared, at x is 1, we've got 1 squared is 1, so its height is 1. However, they knew that that would never be okay because that's way too much area. So jumping back to the textbook, here the first picture shows thinking about the area under the curve between 0 and 1 as two rectangles. So they've nicely cut it in half, and you can see slightly better that they could work out the area of this first rectangle, a half times whatever a half squared is for height, length times its height, and a half times 1. But better than that would be here in this you can see where I'm pointing, here in this second picture they're referring to this as, and they've divided the region from 0 to 1 into 3 rectangles. You can see if we work out the areas of those 3 rectangles, we've still got too much. Going on to 4 rectangles, too much. What the blue is actually showing would be an underestimation for the area. So what if they said, well, let's take the area down at this point. Let's work out the area of the blue rectangle rather than the striped rectangle. But you could see that by taking the areas of the blue rectangles, they don't have enough area. Now, quite cleverly, what they realised was 2 things. They needed to keep on making the size of the, cutting the space into smaller and smaller and smaller rectangles, and that can improve your accuracy. And then they want to see the limit, as you do that, as of the underestimation, the smaller blue rectangles. Let's see what that limit would actually be compared to the limit of the overestimated area from the taller rectangles, and finding the common limit between those two was what they accepted as the area under the curve. Now, the process for doing all of that is, like I said at the beginning, is quite complicated. Hence, they came up with these approximation methods for calculating area. So what I'm showing here in the notes here initially is that the area under the curve by definition is this. It's the limit as the number of rectangles approaches infinity of the upper sum, that's this one, and the limit as n approaches infinity of the underestimation, and the area under the curve is between those two. Okay, well, just like they could see that rectangles gave them some sort of value for the area under the curve, a better shape might be a trapezium. So now you can see the trapezium being constructed. So if we wanted the area under this curve from 0 to 3, yes, you could take one trapezium, but that's not very accurate. Look at all that excess area that would be included in your calculation. So they said, well, if we divided it into 2, that would be better if we divided it into 3, and so on and so on, in terms of increasing the number of actual trapeziums they construct between the limits. And they were getting closer and closer to calculating a fairly accurate approximation for the area under a curve. That became the trapezoidal rule, which is what we are going to focus on here in this next exercise. Actually, in terms of finding areas using rectangles and limits, we're not going to do those calculations. Because like I said, to actually use it thoroughly, we would need to be using some maths that we haven't actually studied yet. You might be wondering why we have a method for approximating the area under a curve when we've got the calculus that enables us to find the area under a curve. Well, it's because we may be faced with a function that it is not possible to actually integrate. End of story. So we have to have some other methods. I'm going to stop the video and actually talk about the trapezoidal rule in another video.